Hello everyone. So this is the week 3 video lecture. I was wanting to go over things pretty quick and get an idea of what's going on in the class. This is a week 3 folder, and this is about organizing your data. So getting the pen out. This is frequencies, and frequency tables are just they're simply counting, right? So like you got in bits for your college majors here. You got 103 for business majors in college. For your natural science majors, you have 82. For your social science majors, you have 137, and just count them as it goes down. Humanities has 93, so on and so forth, for a total of 415. And this is just it's just for another college. See, this is college A. This is college B. So, for example, college B has 3,120 business majors and 2,176 humanities majors, and the same thing for these two as well. Next, we have percentages. So for percentages, all you need to do is which statement is more relatable for this? Of 269 cases handled by the court, 167 result in prison sentences for 5 years or more, or you could just say 62% of all court cases result in prison sentences of 5 years or more. These percentages, they supply a reference for reporting results, so it's like it's easier to conceptualize a percent. So report things in percentages. Your percentage formula is right here. It is your frequency, so the number of, so frequency, how many you have. For example, for the business majors, like so let's say that we had 100 business majors, right? So 100 business majors divided by how many is in your total set. So let's say we had 500, right? We had 500 people total, and of those 500, 100 were business majors, and then we would just divide this. So 100 divided by bring up the calculator just to show the work itself here. So we'll go calculator. So we got 100 divided by 500, which will equal 0.2, and from there we multiply by 100. So times 100. This will be 20%, as you can see here. Going back to the PowerPoint. So that would be divided, so it would be, oops, I thought my pen was active and it wasn't. So this would, convert to 100 divided by 500 would convert to 0.2, and then we multiply by 100, which would equal 20, and then we would just put the percent at the end of it. Alright, so frequency is the number of cases in any category, and the number of cases in all categories is your n, or your sample size, and you can see here the math that's going on. And again, proportions is the same thing, except you just don't divide by one. If you don't multiply by 100. So in the previous example, it'll just be a 0.2 proportion. Pretty easy. Proportions vary between 0 to 1, and proportions. So for the most part, you're going to do percentages, unless it's like this, when you want to just give counts for if it's a small number of cases. You prefer to report the frequencies and the percentages or proportions. And the reason that is, let's say that you have 5 people in a room, right? And of those 5, 4 are white and 1 is black. You would not say in this room, 20% of the room and 20% of the people in this room are black. No, you wouldn't do that, because while this is technically true, 20% of 5 is just one person. Okay, so it would be misleading in a way. Rates. In order to calculate the rate, you need to have the numbers of murders divided by the total population that year times 1,000. This is per 1,000, right? It's per 1K. Now, if you're getting a rate per 100,000, then instead of multiplying by 1,000 here, you would have to multiply by 100,000. So now we have that. So there's another way to summarize the distribution of a single variable. Rates are a number of occurrences of such phenomena divided by the number of possible occurrences by some unit of time. For example, the murder rate can be calculated by this down here, number of murders divided by total population that year, multiplied by however many per number you want, per 1,000, per 10,000, per 100,000. So for every 1,000 people, X amount of murders took place for the year 2004. In other words, you would grab the population for 2004 in the state of Kentucky, so whatever that happens to be, right? So let's say it's, I don't know, 100,000. It's not 100,000, but we're just using this number, okay? And then we take the number of murders. Let's say, I don't know, 400 murders took place in the year 2004. So we would then take 400, divide that by 100,000, and then, that happens first, so it's in parentheses. So let's go back to the calculator. Bringing the calculator back up. So we have 400 murders divided by 100,000. Oops. Let's just clear this out. 400 murders divided by 100,000 give us 0.004. And now let's say that we want to do murder rate per 100,000. We take this number and we multiply it by 100,000. So in this case, the murder rate is 400. Okay. And the reason why it bounced back to the same thing is I divide it by 100. Obviously, if you divide something by 100,000, then to do the opposite. Let's do another example. Let's do the same thing. 400 divided by, and the population is 322,350. All right. Now let's do this again. Clear that. 400 murders divided by the population of 322,350 equal that. Okay, that is scientific notation. Okay. Now we want to multiply this by 100,000. So the murder rate is 12.4 in this case. Okay. 12.4. And it would be the murder rate for this example right down here. So the reason why you would use murder rate or rates is to compare things across populations. For example, it's very unfair to compare the murders in Louisville to the murders in rural Kentucky, mainly because it's a much bigger place. There's a lot more people. So and kind of think of it this way: if Louisville and Paintsville, Kentucky had the same murder rates, then you would actually have there would be more murderers in the population in Paintsville because it's much smaller. You're getting the same rate, but it's much smaller. But it's still the same idea, right? Well, that's not a way to think about it. It's what's a good way? Let me math this out. Okay, so let's bring the calculator up again. Let's say we had a place that had a population of 5,000. Okay. Now let's say that 5,000 had 350 murders in it. So we take 350 murders divided by the population of 5,000, multiply this by 100,000, and we see that place is actually much more dangerous to live with at 7,000 rate, which is insane. Okay, we never want to see that. Now we'll take the same thing. I did what, 5,000? I did. We'll do something I can remember. 300 divided by 5,000 times 100,000. In this example, 6,000. So now let's take that same 300 murders, okay, and put it in a place that has much more population, 525,000. Okay, so let's go 350 divided by 325,003 because it's a much bigger place There we go, and multiply that by 100. And you can see here by rate, this place is much safer to live. I mean, it's still dangerous. 107 murder rates. It's kind of wild. Well, it's not that bad actually, but you know, it's much bigger than what we just got, and that allows us to compare big places to small places. So moving forward, frequency and distributions. It just it kind of granulates it even further. You can say, oh hey, this person was it's hard to read, but I'll read it out for you. Okay, this is the person A is a man, single, and number of services received was 4, age 16. And you know, frequency distributions will break down that granular level of who is this person, what do they do, how old are they, etc. This is how you do it on a nominal level. You got 10 single folks, okay. You got 7 married folks, and 3 divorced folks for a total of 20. And for this is, you know, same deal. 7's married, 13 are not married for a total of 20. This is with ordinal. Remember that ordinal is ranked order. So, you know, this is very satisfied, so it's the highest at 4. And this is very dissatisfied, so it's lowest at 1. And then you have these two, which are in between. And you can see here, there were 4 people that answered very satisfied, 9 that answered satisfied, 4 that answered dissatisfied, and 3 that answered very dissatisfied. They even broke it down in percentage over here, because you have 20 down here, and you know, 4 divided by 20 times 100. That would give you that. More complex than ordinals and nominal tables. These are your interval ratios. These are categories: 18 through 19-year-olds, 20 through 21-year-olds, 22 through 23-year-olds, 24 through 25-year-olds, and 26 through 27. There are 11 18 through 19-year-olds, 5 20 through 21. Something I want you to take notice of here is how these categories, there are 18 and 19, and the next one is not 19 through 20, right? It is 20 through 21, because if you include it, you know, if this was 18 through 20, for example, then 20-year-olds would go in this pile, and 20-year-olds would also go in this pile, and that would double. You would count people twice, which you don't want to do. Same deal here. Count them up. There's a 5, 2, 1, 1. You total them up. They gave the percentages over here. 11 divided by 20. And then you multiply that answer by 100 to get 55%. Same deal, but you know, this is for money. Less than $10,000. Notice that it, you know, it includes 0 and below. This is for, you know, interval ratio. So it doesn't overlap. You can see here it clearly doesn't overlap. And it exhausts every possible option by giving the less than 10,000 and the $200,000 and above. You can see here how many households have that income, how many households have that income. The majority of your households are in here, this little block right here. And looks like, you know, the majority of households are actually right here for the actual category. You can see it's broken down in percentages over here too. Comes out to be 0.1% because someone answered twice, I guess. I don't know. But anyway, so there's a number of ways to represent visually. You got your pie charts, your bar charts, your line charts, your histograms. Here is a sample pie chart. You got 50% single here, 50% divorced, 35% married. Make sure your pie charts are proportional. In other words, because this is a 50% single, half of your pie chart needs to look like this, and it does. This is a good example, of course. And then 15% of your pie chart needs to be divorced if your number is 15%. And then, of course, about a third of the pie chart is married, and you know it does show about a third of the pie chart being married. Bar charts, same deal. You have 10 single people. As you can see, this is category. So category is on your x-axis. This is your x-axis. Okay. And then frequency is your y-axis. So there are 10 people that were single. If you come out to 10 and count over, you see that it lines right up with that. You have, it looks like 7 people that were married. Yep. And then it looks like you have, what is that, 3 people. Yeah, 3 people that were divorced. Same deal when this is like when you have males and females here. So if you look at his U.S. homicide victimization rates by gender, males were victimized more. And if you think about this, it makes sense because crime is homogeneous, meaning the same people commit crimes on the same people. So this includes assault victims, and the majority of assault victims are male because men also attack them. Male on male crime, of course, is higher than anything else in any other stat, male on male. And so you see here that there are more male victims than there are female victims according to this chart by a significant margin. But again, the perpetrator are also usually men. In 1975, it hit a very big high, very disproportionate high. Look at that. Crime went back down in the 80s, and for where we've been going down since. So this is the rate. Remember, we were talking about rates per 100,000. So it was a rate of 12 right here. Same deal. This is also this is histogram. You're just taking the bars, line them up, and you're also kind of crunching them together like it's shown. Like so, it's just shows them. The other way to do this is through a line chart. As you can see, if you do a line chart, it will look, it'll kind of like go through the outline of it, and I'll show you what that looks like. This is just a way to, for interval ratio variables, it's really good for interval ratio variables, and the width of the bar must correspond to the real size of the group measured. So, age of respondent, this is 18 through 20. And there were 40 things in the 18 through 20 category, and then you have this category of like 21 through 22, so on and so forth. The line chart is what we just saw, but it's just plotted as a line. We could have the histograms here just as well. Okay, so that's that. Don't worry about APA. I'm not gonna make you do APA at all. So that leaves us with the study guide for the exam. I'll go over the exam. Get into my downloads real quick. So here we have the study guide for the exam. And as you can see, this has also a shape of distribution, which is part of the exam. So distributions had different shapes, which is skewness and kurtosis. We've gone over skewness and kurtosis in here before. We'll give a small review over it. This is your normal distribution, which I've also gone over before. Oh, I can't edit this because I don't have editing on. Enable editing. There we go. And so we have this. So the normal distribution. This is equal median, equal average, and equal mode. Okay. When you get all three of these things equal number, it produces this little distribution right here. And what goes on here is it's not really an empirical thing, although you will get close to it with like things like height, weight, and when you sample enough people. But let's go further, okay? Then you have what you call standard deviations and normal curve. Again, the normal curve, its mean, median, mode all have the same value. 68%, or about 2/3 of the cases, are located within one standard deviation of the mean. Okay, it is symmetric. That is, left and right side are mirror images. All right, so we have the mirror images. 68% of cases will be within one standard deviation of the mean. So what's a standard deviation on this distribution? Standard deviation on this distribution would be all data points that fall in this case, this area right here. Okay. So let's say we have a single data point right here. Well, we can say this data point is about 0.8, positive 0.8 standard deviation, or z-score. And so just keep this in mind. And when you're asked to draw this normal curve, you want to draw this image here, and you want to label each standard deviation like this is 0, 1, and then we have the 1 and -1. We have the -2 and 2. And then we have the third standard deviation and the -3rd. standard deviation. So, and then here is the tail. The tails are equal. We'll get more into the tails just in a minute. So that's your standard deviation. Standard deviation, kind of like on the distribution here, versus there is a, you have the data standard deviation Excel. It's slightly different, but they are different concepts. Here is skewness. Okay, the one thing I want to point out here for skewness is the tails. These are your tails. Okay, this is a little part. It even looks like a tail. Okay, this is also a tail. So the way this works is the tails are going to be longer on one end or the other. Okay, you're going to have two tails. Like this has actually a second tail over here if you look at it, but this tail's longer, so that's a longer tail. And so a positive skew would have the tail on the positive side. So let's say let's go to our x-axis right here, right? And then there's actually another side to the x-axis. This is the negative side to the x-axis, and this is the positive side. Okay, and so because the tail falls on the positive side, it's called a positive skew. So these are all positively skewed distributions with the tail on the right side or the positive side. So a good thing for an example of positive skew would be income. Most people in the United States do make between $0 and $100,000, and then you have the very wealthy, moving from that with a yearly income of upwards of over $1 million sometimes. Well, and that would be a strong positive skew because the tail it looks really crazy. Okay, so this is a strong positive skew. You can see here modest, moderate, extreme, strong. Here's your negative skews. It's the same deal, except negative. And it means the tail falls on the negative side, like so. And and pregnancy is a example of a negative skew because most of the times these things fall right here. Okay, most pregnancies last 9 months, but sometimes they last over 10 months, and sometimes you got premature babies. Negative skew. Kurtosis is your piquantness, that little pinch up here. That's a high kurtosis. This is a normal, distribution, which is medium kurtosis. This is a low kurtosis. So kurtosis is just your piquantness of your distribution. We're not going to go over z-scores, so don't worry too much about z-scores. This is also z-scores. Now I'm going to go over the exam real quick. I gotta pull it up. Once I pull it up, here's Blackboard. Oops, you're looking at my paste bin. It's okay for you to be looking at it. It's paste bin. So let me pull up this real quick. So here's the exam, and this is the exam for that you'll see. Okay. First thing you'll want to do is you want to draw the wheel science. This can be found on the introductory slides. Identify the 4 level measurements, and I want you to define each one of them. This things like nominal, ordinal, interval, and ratio. Identify three measures of central tendency. Define these terms, mean, median, and mode. What is the difference between descriptives and inferential statistics? Define each of them. 1 second. All right. Now let's see the difference between descriptive and inferential statistics. Okay. Descriptive is describes a population, and inferential infers about it. Things like if you're age 40 through 49, then you are at more risk for heart disease than someone compared to someone that's 18 through 25. That's inferential. Identify three measures of variability dispersion. Define each. Things like range, mean deviation, standard deviation, etc. Describe the following normal distribution: skew, both positive and negative, kurtosis, and then draw a normal distribution. Identify the standard deviations on those distributions. Okay. How does the central limit theorem work? If you remember assignment 1, that's that. What's the difference between sample and population? Okay. Recall the pizza example in class. A pizza is a population. It's a whole pizza. And if you want to draw a sample of it, you want to take a slice. That's a sample. And then I want you to calculate the mean deviation for the set of numbers. There's a set of numbers. And when would you report the median instead of a mean for a variable? Okay. That is the overview of the exam, and it will be posted tomorrow, or well, it will be posted on Monday or Tuesday, and it will be due on Thursday. So that's that. That's the lecture, and thank you.